Hello, everyone, and welcome to the Foundry by Forge College. Let's get right into it. Today's explainer is all about the Anchor Rust programming model. If you've ever felt completely overwhelmed by the sheer mechanics of building on Solana, well, you're definitely in the right place. We're going to decode exactly how Anchor takes a wildly complex process and turns it into an elegant, structured, and totally safe engineering marvel. I like to think of it as a tour of the master blueprint for Solana development. Okay, let's dive into this. Think back to our previous lesson where we mapped out our anchor.toml file and confirmed our program IDs. That was our foundation, right? Now contrast that with writing raw Solana Rust code. Honestly, it's kind of like managing a chaotic construction site. Every single brick, wire, and pipe has to be manually checked, indexed, and routed by you. It's exhausting, soul-crushing manual plumbing. But with the Anchor framework, we get this declarative, safe master blueprint. Instead of writing all that paranoid defensive boilerplate code just to make sure someone isn't tricking your program, Anchor literally lets you just declare what you want, and it handles all the heavy lifting for you. So here is our schematic for today. We'll be looking at 1. Core abstractions, 2. The handler anatomy, 3. Account flow, 4. CPIs, and finally, 5. Key takeaways. This will perfectly prep you for writing your own smart contracts. All right, let's kick things off with Section 1, Core Abstractions. These are the high-leverage building blocks that completely change how we organize our logic. The first massive tool in our toolkit is the derive accounts macro. I really want you to imagine this macro as the ultimate unforgiving bouncer at the door of the most exclusive club in town. No shoes, no shirt, no valid signer status? Yeah, you're not getting in. Before any of your actual business logic is allowed to run, this bouncer generates a runtime verifier that relentlessly checks everyone's IDs. Are you actually a signer? Are you authorized to be writable? Do you have the right ownership? If an account doesn't meet the strict criteria you declared, the bouncer violently throws the transaction out before it even steps foot inside your program. It's an absolutely crucial security blanket. Okay, so once you actually make it past the bouncer, you're handed a context wrapper. Think of this as a beautifully organized, neatly packed bento box of pre-verified accounts. It bundles all those validated accounts and instruction data into one single safe surface. Your handler doesn't need to go hunting for data or double-checking if it's actually safe to use. It just calmly consumes what's in the bento box and gets straight to the state mutations. Now, what's really interesting about this slide is how Anchor's terminology maps directly to the raw Solana primitives underneath. It demystifies the whole magic of it all. That context we just talked about, it's really just bundling raw instruction accounts and data. The derive accounts macro, it's handling the account metas order and validation. And typed wrappers like account and program, they literally take raw byte slices of data and deserialize them into actual usable Rust types while strictly enforcing ownership. It perfectly bridges the gap between raw, hardware-level logic and human-readable architecture. Moving right along to Section 2, the instruction handler anatomy. Let's look at a real working code schematic for a canonical deposit handler. First up, look at this state definition. We've got a simple vault struct holding an owner pub key and a balance. But the real star here is that account attribute right at the top. By adding just that one little line, Anchor automatically handles all the serialization and deserialization layout for this vault state. You don't have to manually count bytes or shift bits around. Anchor just ensures it's packed and unpacked perfectly every single time. Next, we define the inputs for a deposit function using our bouncer, the derive accounts macro. Look at the declarative constraints we've set up here. We're telling Anchor that the user must be both mutable and a signer. We're also telling it that the vault must be mutable, and we apply a has1=owner constraint. That simply means the vault's owner has to exactly match the user executing the transaction. If that signer bit is missing on the client side, or if that has1 check fails, Anchor throws a clear, readable error before your deposit code ever even thinks about running. So the crucial point is right here inside the actual handler function. Notice how flawlessly clean our public deposit function is. You receive your context bento box, and you just do a simple checked add to the balance. That's it. You're just working with safe, deserialized types. There's no manual iteration over account arrays, no paranoid checking if the account belongs to the right program. All of that was handled by the constraints, which lets you focus 100% on your domain logic. And just briefly, to round out our handler, Anchor also elegantly takes care of the operational side of things. It handles structured, indexable logs via the emit macro, so off-chain clients can easily track events. And it lets you map failures to custom, highly readable errors using the error code macro. So no more cryptic error number 42. You get a clean, obvious overflow when adding balance message. All right, let's zoom out a bit for Section 3, tracing the account flow. As a quick aside, if you want to explore broader architecture patterns like this, we have some fantastic adjacent courses in the Forge College curriculum. There are 3 mental layers you really need to master for this flow. Step 1 is the client transaction. Crucially, the client still has to supply the account metas in the exact sequence that Anchor expects. Step 2 is the Anchor verifier, our bouncer, which receives those accounts, applies our strict constraints, and deserializes the data. Step 3 is the handler logic, where your code safely mutates the state. The order is strict, and understanding this flow is exactly how you'll debug issues when the client invariably sends accounts in the wrong order. But here's a fun question. How do we safely hire a subcontractor using our blueprint? Like, what happens when our program needs to ask another program to do something on its behalf? Say, moving an SPL token. Which brings us perfectly to Section 4, cross-program invocations, or CPIs. And this brilliantly illustrates Anchor's core design philosophy, the call-up context. It makes calling other programs drastically simpler than manual instruction building. To call another program, Anchor reuses the exact same typed context pattern we just learned. A call-up context simply borrows your already verified accounts, safely repackages them, and attaches any necessary signer seeds for the program you're calling. You don't have to learn a completely new system to interact with other contracts. You literally just pack a new bento box for the callee. To make CPIs work smoothly, there is a very strict division of labor. The caller, that's your program, is responsible for providing the account metas in the correct order, supplying any signer seeds for PDAs, and building the CPI context. The callee, the program you are talking to, is responsible for declaring its own parameters, validating ownership, and deserializing the state. It's a clean handshake. Both sides know exactly what they are responsible for, so you know exactly where to coordinate your client, caller, and callee plumbing. And that brings us to Section 5, wrapping up our schematics and looking at the key takeaways. Here are your 3 main takeaways from today. First, Anchor relies on declaration-first validation. You write your handlers with the total confidence that if the code is running, your declared constraints have already been enforced. Second, typed wrappers keep your focus entirely on state transitions. This heavily reduces off-by-index bugs and eliminates the need for tedious defensive programming. And third, CPIs reuse those exact same typed account patterns, making cross-program interactions an absolute breeze. Let's move to and see how this builds our foundation for what's coming next. In our upcoming explainer, we're going to dive into common program idioms. We'll be looking at things like PDA-based authorities, rent-exempt account creation, and how to structure much more complex account relationships. You now have the underlying mental model needed to tackle those advanced patterns. So I leave you with this question. Are you ready to start building your own on-chain blueprints? Because with Anchor's Rust programming model, you have the most powerful tools available to make it happen securely and efficiently. To dive deeper into this subject, explore more courses in the Solana Development Tools track, and truly accelerate your Web3 journey, make sure to visit forge.college. This explainer was brought to you by Forge College. I'm your host, and I absolutely can't wait to see what you build. Catch you in the next one.